The following is a partial review of the physical behavior of matter topic that you will encounter on the New York State Chemistry Regents exam. Let's begin with states of matter. There are actually three states of matter: solids, liquids, and gases. Solids consist of vibrating particles that are in fixed positions, forming a rigid crystalline structure. Liquids consist of particles that are mobile and can slide past each other, while gases consist of particles that move in random straight lines. Matter may consist of only one substance or a combination of substances. Matter consisting of only one substance is called a pure substance. Elements and compounds are examples of pure substances. Matter consisting of a combination of different substances are called mixtures. Mixtures may be homogeneous or heterogeneous. Homogeneous mixtures are called solutions. Examples of solutions include brass, a combination of copper and zinc, and seawater, a combination of sodium chloride and water. An example of a heterogeneous mixture includes a fruit salad or salt and pepper mixtures. Consider the following example. Which sample or samples do or does not represent a pure substance? From the key, three elements are being shown: an X-centered element, a shaded element, and an unshaded element, labeled X, Y, and Z, respectively. In sample 1, we see a combination of X-centered elements and shaded elements. In sample 2, we see a combination of shaded and unshaded elements. But in sample 3, we see all unshaded elements. Therefore, the samples that do not represent pure substances are samples 1 and 2. Now for an explanation of temperature. Temperature is a measure of heat energy. Standard temperature is 0 degrees Celsius or 273 K. To convert from K to degrees Celsius and vice versa, use the formula K is equal to degrees Celsius plus 273. Since the Kelvin scale and the Celsius scale differ by a value of 273, the difference between 20 degrees Celsius and 40 degrees Celsius is the same as the difference between 293 K and 313 K. Temperatures on the Celsius scale and the Kelvin scale will always differ by the same amount. Now for a brief review of energy. Energy is classified as potential energy or kinetic energy. Potential energy is stored energy, while kinetic energy is the energy of motion. Average kinetic energy is an indication of the speed that particles of a substance are moving or vibrating due to the input or extraction of heat energy. Average kinetic energy represents the temperature of a substance. Therefore, if the temperature of a substance increases, the average kinetic energy of the substance also increases. So in a choice between 100 grams of water at 30 degrees Celsius and 5 grams of water at 90 degrees Celsius, the 5 grams of water has the highest average kinetic energy because it has the higher temperature. Since the average kinetic energy of a substance only relates to its temperature, the amount of the substance does not matter in terms of average kinetic energy. Now for a specific type of energy, heat energy, also known as enthalpy. Heat energy, or enthalpy, always flows from a warm object to a cool object. So if a warm object is placed beside a cool object, the heat, or enthalpy, also labeled as lowercase q, will flow from the warm object to the cool object. So if substance A at 60 degrees is placed in contact with substance B at 20 degrees C, the heat or enthalpy will flow from substance A to substance B. Now for enthalpy calculations. When calculating the amount of heat energy or enthalpy transferred during a process, use one of three formulas found on Table T. If the problem contains a temperature change, use the formula Q, or enthalpy, is equal to mc delta T, where m represents the mass, C represents the specific heat capacity, usually of water, and delta T represents the change in temperature. Consider the following example. If a substance is placed or added to 25 grams of water at 10 degrees Celsius and the temperature of the water increases to 80 degrees Celsius, how many joules of heat energy did the water absorb? The formula to use to determine the amount of enthalpy transferred is found on Table T in the heat section. The formula Q is equal to mc delta T should be used to determine the amount of heat energy transferred or absorbed. Now input the data into the formula and multiply. This generates the following, where Q, or enthalpy, will equal 25 grams of water times the specific heat capacity of water, 4.18 joules per gram times degree C, times the delta T, which will be 70 degrees. After canceling the units, the final answer will be 7,315 joules. Finally, phase changes and the heating curve. All substances will undergo phase changes at a particular pressure during the application or extraction of an appropriate amount of heat energy. The phase and temperature changes that a substance undergoes during the addition of heat energy may be plotted to generate a heating curve. The heating curve of a substance represents an endothermic process. The following explanation only applies to the heating curve of a sample of water at 1 atmosphere of pressure or standard pressure. Energy changes and the heating curve of water. This image represents the basic profile of a heating curve where a substance is being heated uniformly over time. During line segment AB, average kinetic energy is increasing, but the potential energy remains constant. During line segment BC, the potential energy increases as the substance absorbs more heat energy as the average kinetic energy remains constant. If this substance was indeed water, this phase change, also called fusion, would occur at 0 degrees Celsius or 273 K. During line segment CD, the average kinetic energy or temperature once again increases, and the potential energy yet again remains constant. During line segment DE, which occurs at the boiling point of the substance, the potential energy once again increases as the average kinetic energy remains constant. If this substance was indeed water, this phase change would occur at the boiling point, 100 degrees Celsius at 1 atmosphere of pressure. During line segment EF, the average kinetic energy again increases as the potential energy remains constant. This image represents the reverse, or the release of heat energy during a phase change known as crystallization. When a substance changes from a liquid to a solid, which is known as crystallization, the process is now exothermic. And when a substance changes from a gas to a liquid, which is known as condensation, the process is also exothermic. When a substance changes from a liquid to a gas or undergoes vaporization, the process is endothermic. And finally, when a substance changes from a solid to a liquid or undergoes fusion, the process is endothermic.